I'm sure people know, but Epic Games was created in 1991 and went on to transform the gaming industry several times, one of which is Unreal Engine. So let's talk to the origin story of that. You said that when Wolfenstein and Doom came out, that changed everything. So take me to that moment.
Yeah, that was a very interesting time. Epic had, after my first couple of games, had recruited developers, usually college students, high school students who are just working on their own, had real skills, but didn't have an outlet for their work. Epic had been matchmaking the best artists and programmers together from all over the world. Like Jazz Jackrabbit was Cliff Bleszinski, a high school kid in California who'd made a really cool adventure game together with Ariane Brucey, a demo coder from Holland who'd make amazing graphical stuff and had built a 2D game engine. And it connected them together, and a musician, Robert Allen in California, and by telephone and modem and so on, we were building these little 2D games and having quite a lot of success. There were a bunch of people making thousands of dollars a month while they were still students, and royalties from the games that Epic was kind of producing and by coordinating people with people and publishing through shareware. Um, and that was all going great. And the company had a little office, and we were, copying floppy disks and mailing them out. But when Wolfenstein came out, we realized like the future of gaming is going to be 3D. It, there had been a lot of experiments in 3D before that hadn't been great. There were 3D renderings of mazes that were not in real time, and you were always looking north, south, east, or west. And then there were vector graphics with little wireframes moving around and things. But Wolfenstein was the first game that was fast enough, running at 30 frames per second. It really felt immersive. It felt like you were there, like you were, in this castle Wolfenstein fighting Nazis, and that was a really amazing and immersive experience. 3D graphics were pretty primitive then. Id Software followed shockingly fast with Doom, which was a much, much more capable 3D engine, which had, stairs and though it was still what we call 2.5D, it was environments that were very realistic, textures that were very realistic, a form of lighting that was approximate but incredibly realistic, and just such great artistry and sound effects. It felt completely visceral and real. You know, you might look at it today from our point of view of a modern game player with 20 teraflops of computing power in your device and say, oh, that's not very impressive, but it was amazing at the time.
I mean, for me, just decide to pause on that. I think Wolfenstein was one of the most amazing moments in my own life. Just being able to, like you said, in real time, move about a three-dimensional world. I just remember just moving around, just in like, what is that feeling like? I mean, you feel transported into another world.
You feel that you're there, yeah,
Yeah.
and especially you turn the lights down in your room and you turn the sound up on your speakers, and it will scare you, and you'll feel like that fireball that's coming at you is going to kill you.
Yeah.
That was an amazing time because we hadn't experienced that before. There was nothing like that. Uh, you'd watch a movie, a scary movie or whatever, but it was just this thing that was happening. This was you. This was you in a 3D world.
So, how did that change Epic? This realization that the future of gaming is going to be 3D.
Well, at first I was really depressed. I think because
Yeah.
the wizardry of Doom especially was so incredible that I gave up on programming for like 6 months. I was like, "I'll never be able to compete with this. I have no idea what we're gonna do." We just keep making 2D games and hope that the business goes on, but, like, that was the nature of Carmack's wizardry. He had done things that were, like, not just one innovation leap ahead, but, like, a dozen simultaneously,
Mhm.
interplaying in a way that you couldn't pick them apart into their component pieces. But, funny thing happened, Michael Abrash, long-timer in computer graphics, wrote a book on the techniques for 3D graphics and texture mapping, and he wrote some articles in one of the programming magazines of the day, and explained it and showed assembly code to do texture mapping, drawing these 3D graphics on the screen, and it was actually really simple stuff. I was like, oh, I can do that, and so a bunch of us at Epic independently went off and started writing our own 3D graphics code to figure it out, and uh, we found at one point we had a number of people dabbling in this, doing different parts of it, and at that point we decided, okay, this is 3D graphics and 3D gaming is gonna completely change the world. We need to go all in on this." And so we took the best people from our best 2D game development teams and put them all together to make a 3D game. Um, we didn't really know what we were doing at the time. None of us had ever shipped a 3D game, and most of us were still learning, but, everybody was, like, trying different disciplines to see what they were best at, and, it was a combination of a bunch of people, who came together to make Unreal. I'd initially volunteered to make the 3D editor, for the thing, and James Schmaltz had made Epic Pinball. Epic Pinball, now that wasn't a crazy game, this was one of the 2D shareware games. He made it while he was in college, and he was making, like, $30,000 a month from, the royalties from this game because
Wow.
everybody had wanted an awesome pinball game. It's massively successful, but, he was a multidisciplinary person. He wrote the code for the game, the art for the game, and did basically everything, and the code was 30,000 lines of assembly language. And so, he was initially gonna write the 3D engine, and I was gonna write the editor, and he sent me his code, so I could integrate it into the editor, and it was, like, just a giant pile of assembly code. I was like, "Hmm, why don't I just write this myself?" And so James instead started going off and building 3D models and 3D animations using the tools at the time, and so Cliff, who'd done a lot of design work and built the levels on Jazz Jackrabbit, went off and started learning basics of level design. And so I was writing this editor, and Cliff Blazinski was customer number one for it, starting to go off and build levels. And James Schmaltz was building awesome creatures, sending them to me. I'd get them implemented in game. And then we brought in an animator to bring them into life. And we brought in more and more people until at the peak of Unreal 1 development, we had about 20 people working on it, which was a huge team for the time, and was really stretching Epic's finances nearly to the breaking point.
Mhm.
We barely survived and almost ran out of money a number of times, but somehow we always pulled through. And it was a crazy project because it was 3.5 years of development and a game that we always thought was 6 months from shipping. And it was like 3.5 years of 70 or 80-hour weeks for most everybody working on the project. Not even knowing what problems we'd need to solve next because we were so immersed in the current ones.
Were there moments when you were losing hope that this might take too long and the company will run out of money?
We were, we were always very financially stressed, so I was continually worried about that. I had total confidence though that we'd work out all the technical and artistic problems because we knew the pieces, and it was largely a matter of typing code in and solving some problems. And kind of like we knew we could ship a version of it. And the thing that was continually really interesting was the ongoing discovery of new techniques as we went. Because at the time Quake had shipped, it had a little bit of dynamic lighting. Unreal really pushed dynamic lighting much higher than anybody else had done before. Having colored dynamic lights with some shadow casting capabilities statically, or moving lights without shadows, and figured out how to do volumetric fog, so you could have foggy areas that were full of lights, and you get the kind of glow of the lights standing out in the fog and affecting the appearance of the level. A whole lot of amazing techniques came together to build a game that made a number of leaps ahead of the state of the art at the time. Um, uh, yeah, it was really crazy, but like I think most companies wouldn't have survived that, but the sheer talent of the people involved made it possible. And that's Epic has often done things that most companies would have failed at, and we succeed, like, not because of awesome management or awesome planning, or awesome financing, but because of the sheer talent and willpower of the people involved to make it happen.
What about the interdisciplinary aspect of it? Like you said, sort of artists, engineers, or programmers, designers, all of them working together. What was that? The 20 people. What was the dynamic there like? Working insane hours. Like, what was it like to sort of make a team like that work together well as an orchestra to actually deliver the game?
Yeah, that's one of the really unique things that exist in gaming, not in normal big tech companies, which are just engineering and business driven, but gaming really does require all of the best people across all of the creative disciplines working together. And Epic had grown organically by recruiting people with awesome talent. We always had a limited budget. We could never pay to hire, bid up people's salaries and hire them away by paying them more. We just had to find awesome people who were at the beginning of their career and put them together. And so everybody was very new to this. and didn't have any assumptions about how companies worked. And so, you put all these people together, and that it was really a constant interplay of talent as people were learning how to work together as a team. Like nobody had management experience. Most people hadn't shipped a game before they worked with Epic, and we were figuring out as we went. But it was a constant iterative cycle. We'd make several new versions of the game every day. It'd be a new compile, introduce a new feature, or fix some bugs, get it to the artist. The artist improve their levels, continue building stuff, and then we see what they're doing in their levels. Like, I see what you need now. We'd constantly be improving the tools, and just the iterative process and the speed at which that improves products is the critical element to success in games. The slower the iteration cycle, if you make a build every week, and you go through one iteration every week, you're gonna be way, way, way worse by the end of your project than a game company that makes, new stuff every day. And, yeah, that was the magic that happened together, and it wasn't there was really nothing but passion and everybody's individual dedication to it that made it work.
I heard you still program, but how much programming were you doing back then? You mentioned the hours, probably insane hours. So like, it'd be almost fun to talk about your setup. What a day in the life of Tim Sweeney in the '90s when you're building Unreal looked like.
Well, we'd all gravitated towards a work schedule that maximized productivity, and that usually meant waking up late. I usually get to work around noon, and usually work till, like, 2 AM or so, 3 AM sometimes, and,
Nice.
I didn't have anything else going on in my life, so it was really just work and sleep and occasional eating, and, uh, I found I always needed 8 or 9 hours of sleep a night. Without good sleep, I would just become a zombie and wouldn't be nearly at my best. So I always needed to get sleep, but I didn't need anything else going on. So the programming itself was so energizing and enthralling. Um, yeah, so it was 3.5 years of that during the project. Mostly spent programming. I'd say probably 60 hours a week of programming, 5 hours a week of coordinating with other people and iterating and sitting down with them and looking at what's going on in screen and figuring out what they needed. Maybe 5 hours of business stuff. There's a good division of labor then. I didn't have a big executive team, but it was like basically myself running the technical and development part of the company, and Mark Rain running the business part of it, doing deals and maxing out his credit card and going around the world bringing in sources of revenue to keep the company funded.
What programming language are we talking about? C? Because you mentioned there's this pile of assembly. Did you what was your decision in choosing the programming language that Unreal Engine would be written in?
I'd grown up learning with Pascal as my favorite language.
Nice.
In order to just get maximum performance and get the latest operating system features, I had to move to C, for my second game, Joel of the Jungle, a little Nintendo-style platformer, and so when I started Unreal Engine, it was on 16-bit Windows using the C programming language, and, over the course of the first year, it moved to 32-bit, using these DOS extenders and then using Windows NT, and I moved to the C++ language, and just because it simplified the code so much. Went from a really complicated pile of code to a much simpler one, making that transition. And so almost the entirety of Unreal Engine development, about 2.5 years of it, was all in C++, 32-bit, completely state of the art then. Like 32-bit protected mode was kind of a magical thing, having come from the days when computers were much less reliable and crashed all the time.
Yeah, and turned out to be a pretty good bet because C++ out of all those languages ended up being the dominant sort of performance-oriented language that survives to this day.
Yeah, yeah, it's because it solves all of the problems at scale, often through manual pain, but always solves them. And a
Yeah.
lot of other languages do better in a lot of like theoretical aspects and are better for some usage cases, but you can't do everything, and that's really very limiting.
All right, so ridiculous questions, but like, did you have one monitor, two monitors? Were you picky on the keyboard? Were you
Okay,
picky on the chair? What are we talking about? Let's paint a picture.
okay, I went through a big transition there. So I started
Okay,
out
great.
being pretty lazy. I'd had a bunch of like I bought used computers because you'd often get them at half the price of a new one. They'd be good enough. So I had this old 486 I was developing on. I guess it was a 15-inch monitor at the time. It was a poor workstation setup, but it was very economical. And so as we started on Unreal, I realized that I had to write a ton of code. I had to write it at absolute maximum productivity. So I had to rearrange my entire life around delivering maximum output. And so at that point, I realized like actually spending money on getting good equipment was a good investment. And we're not talking about millions of dollars here, or billions if you're building a GPU farm. We're just talking about buying some basic hardware. And so I bought the biggest CRT you could buy at the time because this was a CRT era. It was 24 inches. It weighed like 100 pounds. I had back pain for a week after I installed it, but it got me 1920 by 1200 view
Wow,
in
nice. State of the art.
1996. In 1996, that was pretty cool. So I'd upgraded to a 90 megahertz Pentium and did a lot of programming on that. It was on the 90 megahertz. These were the main consumer computers at the time, and I'd optimized the Unreal Engine software render on that, which was, you know, the Pentium was the first scalar architecture in consumer computing. It could run up to 2 instructions at a time, and if you wrote your assembly code very carefully, you could get absolute maximum throughput. So I'd gotten my texture mapping code down to 6 CPU cycles comprising 11 instructions. That was required for every pixel on the screen, and that was just enough performance to deliver that. Um, but Dell came out with these new workstations, and Intel had just launched the Pentium Pro, the first out-of-order processor. Um, and so I like basically bought the absolute maximum configuration that money can buy. It cost $7,000. I had a gigabyte of memory in
Nice.
1996, and a 200
Wow.
megahertz CPU. So it like tripled the speed of compiles and just made me massively more productive. So that's why I was using throughout Unreal Engine development and shipped with that.
By the way, people in the 90s would have been blown away by this workstation. I love it. Yeah, yeah. Were you, in writing, were you considering the hardware much? Was there a sense like, for people who don't know, Unreal Engine rendering, I guess, is all software, it doesn't use the hardware. But were you trying to optimize, as I understand, maybe you can correct me, but like, were you trying to optimize to the hardware at all?
Well, at the time, so we did most Unreal Engine development before the first real GPUs came out. And the 3D Voodoo one, the first GPU that actually delivered serious performance compared to software rendering. The first GPU that was really gainful came in the end of the development, and we supported it really quickly, but it was not the target all along.
Hmm.
And so development was focused on just building. There are two parts of the engine, right? There's all of the gameplay systems that manage the simulation and physics and so on. That's all written in very high level C++ code. And maintainability is as much of a goal as performance, because we had to build massive amounts of systems over time. But there were one thing that was really a bottleneck was graphics. The cost of rendering a single pixel was really high, and so you had to do everything you possibly could to optimize the rendering of pixels on screen. And so we were talking about how many CPU cycles. When you say your CPU runs at a gigahertz or whatever, that's a billion instructions per second. How many instructions do you need to run to get a pixel on screen? And so there was a constant challenge to optimize that down. And there was also a competition among all of the graphics programmers who'd often send emails, like bragging to each other about what new technique they've discovered, to try to get the cost down. And Abrash's original articles took like 12 CPU cycles to render a pixel, and everybody else had figured out how to get it to like down to 6 or sometimes even 4 cycles. And that involved lots of different trade-offs of caching and memory hierarchy and so on. It was just like a magical time where a human could actually understand exactly what the CPU was doing under the hood and could write code that exactly targeted that. Um, and that's largely lost now. When we talk about optimization and software now, it's largely about heuristics and statistically, this memory access is likely to hit the cache. And this algorithm is faster than that algorithm. Because CPUs now have such advanced out-of-order execution that you really can't micromanage what's happening on an instruction by instruction basis. You can only manage the aggregate performance of code. And so there's kind of this lost art. Some people miss it, some people don't, in which the programmer had absolute control over the machine and could work miracles in special cases if you tried.
It seems like there's still value to that art when it comes to GPUs and ASICs. So basically, trying to understand the nuances of the hardware and how to truly, truly optimize it, whether it's for machine learning applications or for ultra realistic real time graphics applications. Is that true?
Yeah, that's absolutely so. The optimization problems have just moved around.
Yeah.
In a system like Nanite, the virtualized micropolygon geometry system that Brian Karras, a brilliant engineer with Epic, built, was just one of those multi-year optimization efforts that required understanding everything from the highest levels to the lowest levels of the hardware to figure out how to make this breakthrough technique work in a way that was actually maximally performant on GPUs.
And so Nanite is the system, we'll jump around in time. That takes us to today with Unreal Engine 5. This the system that does the geometry.
Yeah,
So rendering the world sort of geometrically. There's many layers to this. We'll probably sneak up to each of those. But one, you have to actually create the geometry of the world around you and do that in real time and really efficiently. And there's a bunch of different ways to optimize that. Can you just speak to it?
yeah. With the advanced art tools we have today, it's really easy to create a scene with billions of polygons. The hard part is how to render it efficiently, because you can't render billions of polygons in a frame. Basically, you want to render an image that's indistinguishable from the full detailed geometry if you rendered it at ridiculous cost. And so the challenge is how to simplify every component of the rendering, the geometry, the lighting, and so on, down to real-time techniques. They're efficient, they capture a realistic view of what's around you. And so when an object is up close to you, want to render it with a lot more polygons than when it's far away. But one of the cool principles of mathematics is the Nyquist sampling theorem that says if you're trying to reconstruct a signal, there's a limit to the amount of data you need to bother capturing. If you want to render a texture at a certain resolution, then you never need more than twice the pixels than in the texture that you have on the screen. Um, and that's called the Nyquist limit. And so one of the challenges of computer graphics is given the need to render objects at extreme close-up distances and extreme far-away distances. You always want to be able to generate the right amount of geometry so that you have enough to be indistinguishable from reality, but not any more than necessary. And with geometry, the idea is that if you render two triangles per pixel, you should get an image that is indistinguishable from thousands of triangles per pixel. If you render less than two triangles per pixel, you're going to start to see visible artifacts of the loss. And GPUs have this amazing hardware in a lot of different pipelines, but it's all very fixed function. There's pixel shader hardware, there's geometry processing hardware, and then there's triangle rasterization hardware. And one of the limits of GPUs is that the triangle rasterizers are built for pretty large triangles. If you're building a triangle or rendering a triangle with 10 pixels, that's pretty efficient. But if you're building or rendering a triangle with 1 pixel, it's very inefficient. So one of the breakthroughs Brian made was to design an entire pipeline for avoiding the rasterization hardware in the GPU and just going straight to pixels and calculating what should be done with that pixel as a result of some ray tracing and uh, geometry intersection calculations done in a pixel shader. So instead of using the triangle pipeline, we're just using the pixel pipeline and
Wow.
getting a better result.
Because of the limitations of the triangle rasterizer in the GPUs. That's fascinating. Because as you described, you need the tiny triangles for the detail, for the stuff that's up close. I mean, this might seem obvious to people, but it's not just stuff up close. It's like it depends on where you're looking, like the human eye and the human focus and the human attention mechanism uh, defines how much detail you want to show. Because the thing that the human is likely to be giving attention to, you want that to be super high resolution. And everything else, including due to distance, can have less geometry, less texture, less information in it.
Yeah, that's right. But there's a lot of challenges like that. It turns out it's a lot easier to render one frame that looks perfect than it is to render a series of frames in motion that look perfect. A lot of the problems with the earlier algorithms that aspired to do this sort of things was popping. You'd be running some number of triangles for a while, and then you'd switch to a different number of triangles, and you'd see a visible transition, and screen would look like it got shaken up. It's a disturbing artifact that distracts you from the game. And so one of the magical trade-offs of Nanite was how to avoid all of the visible transitions, um, and get them down to a point where, uh, though they exist statistically, they're not really perceptible to a person looking at it.
You look at something like Nanite, I mean, there's a nice blog post, there's nice descriptions about the details, but you can tell even under the details, there's just incredible engineering that goes on. It's so cool. It's so cool how underneath this, the actual experience of beautiful, detailed scenery, there's just incredible engineering to bring to you simulation, ultra realistic simulation of reality in real time, with like lights changing everything. And then, it just takes you back to that feeling I had with Wolfenstein, but like more. And you can completely lose yourself in that world and you would forget that this real world exists. What is the real world anyway? So it's that coupling of great engineering and great storytelling in terms of just feeling is super cool. It's great to know. It's great to know that these teams behind it, and it's cool that you're also releasing a bunch of details around it. At least for folks like me, it's inspiring to see.